Hello everyone, this is Johan Mattsson speaking, and I will hold this lecture about biodeterioration in temperate climate. This presentation is a more thoroughly information about this topic, and maybe you already have seen the short version in the introduction video, but if you're looking now, you will hopefully learn more about the details. This is a map of where I assume you are sitting right now and listening for this. So as you can see, it's a good distribution all around the world, and by that reason you also have very different experience of what can be the problem with biodeterioration. But still, hopefully you learn through this presentation that you also have a lot in common about these aspects, because at the general level, it's very much similar issues, no matter if you're sitting in Canada or Colombia or Philippines or in Finland. So this is typically something you have to understand at a general level in order to be able to manage it in the specific level afterwards. I work in the company here in Oslo, and we are all the time working with biodeterioration in different aspects. We have been working, we started this company in '86, so we've been working for 35 years, and we are about, well, almost 40 persons, and most of us are biologists. So we have this approach of looking into different problems as with a biological view. And that can be very useful, because otherwise, if it's civil engineers, people or architects, they have a lot of understanding, but not about these specific issues that fungi and insects are depending on. As you can see on the map, this is a part of the central part of Oslo, and the spots are marked where we have been to investigation of possible problems in buildings. So you can see that it is a lot of questions about these topics, and it's also typically how much you can really find problems if you're looking for them. So one issue is to understand what is serious problems and what is not so serious and not so complicated. And we also look a lot of do a lot of analysis on the materials, wooden samples and air sampling and other materials that have a possible contamination. I am, as I said, biologist, and I have been studying mycology at the University in Oslo many years ago. And in later years, I took a doctor degree at the university in Trondheim with the topic of the impact of microclimate at biodeterioration of wood in historic buildings. This thesis is available for you as a PDF, so I encourage you to read at least the abstract and the introduction, and if you got to get inspired, you hopefully read a bit more, but at least you can get a lot of general understanding in the introduction chapter. So, and yeah, and also I have a very practical approach for issues. I'm very much out in buildings looking and for reasons for why damages has occurred, and the solutions for how to handle a possible damage. But also, of course, it's not only old buildings. We can find biodeterioration problems in all kinds of buildings, in new concrete constructions, and of course in other constructions as well. So I've been offshore sometimes in steel constructions, looking for not fungal deteriorating, but mold problems. So this is a universal problem you can find in all kind of situations, and of course it's more interesting to work with old buildings. So we have at least I have a special interest in old buildings, and of course, if they're still standing there, it has been a lot of exposure and a lot of damages occurring all the time. And the building has been standing there. So reading the building, both where you find damages, where you find absence of damages, and where you find repaired materials, is a lot of important information for you to understand how is this building working, and where is the weak points, and what can be done in order to avoid the damages. The oldest building, wooden building in the world, is this pagoda in Japan. It was erected, I'm quite sure it was in 607, but there was some literature suggesting 5 years later, but nevertheless it's a very old building. And still this pagoda is, when I was there, they said it was like 60 to 70% of the wooden materials is original. So wood can have a very long service life if it's a good construction, if there's good maintenance, and if there's a bit luck, of course, then wood can have a very good service life in standing buildings. But of course, the wood in forest in nature is supposed to decay sooner or later, because it's a natural circulation of carbon and other substances. So of course it's supposed to be decayed sooner or later, but in buildings we would really like it to be later than sooner. So we can see that this is and expect that this will happen. But of course the question is, how can we prolong the service life, and what can be done if we see that it's a problem with some deterioration? And to this, the main answer is knowledge. We have to understand what is biodeterioration, what is the causes for biodeterioration, and what can be done for avoiding that. The problem is that it's a lot of different species that causes this kind of different kind of damages. So it can be complicated in one way if you go too much into detail. But for many insects and of course all fungi, you can generalize the issue and say that dry wood will not deteriorate. The problem occurs for pine and spruce, which is main wooden materials in Scandinavian country, is typically when you have a moisture content above 20%. Then it's a possibility for the fungal activity, and then we can have a problem. But of course, keeping the wood dry doesn't have to be very complicated. It can be done just by good constructions, by some layers that keep the water away from the main construction, and also surface treatment, for instance, can keep the wood dry, and for that reason many of the materials are safe. But of course there are some species, like in Scandinavia we have this house longhorn beetle, Hylotrypis spiolus, that can to some extent also develop in quite dry materials, even though this is not the favorable spot for the insect. They can handle the dry conditions quite well. But just looking into the nature, out in the nature, we can see the pattern of deterioration very clear. If you see a trunk or just some other materials, you can see very soon where the moisture content is more favorable and where the biological activity are occurring. So you can see that this is typically the sapwood that is the most attractive for biological activity, in meaning of deterioration. You can see the same pattern in the logs that has been exposed for a long period. You see that the decay is occurring in the sapwood, not in the heartwood. So we can understand that the material quality has some importance in order to avoid biodeterioration. But we see the same pattern as well in buildings. We can see that some materials are more sensible for biodeterioration, and some part of the wood might be more deteriorated than other parts. Like this beam, you can see that the surface is quite unharmed, but the problem is that this is just a few millimeters, and then the internal part is completely deteriorated. So of course, when you reach that level of deterioration, the materials is completely lost. We have to understand the main factors, what is causing the possibility for biodeterioration. And in order to not making it too complicated, I used to simplify it and say that we need just a few factors. It's 4 main factors that is the crucial issue if it's going to be any biodeterioration or not. Of course, fungi and insects, as well as we, need some nutrition in order to survive. These specific species are really experts in digesting and deteriorate cellulose in the wood. And of course, since cellulose is a major part of the wood, the consequences can be huge if they are really deteriorate that part of the wood. But in order to have a deterioration, most of the organism needs a sufficient amount of water in order to survive and to deteriorate the material. It's very, very rare that the organism can deteriorate dry wood. And so this is a main factor as well as nutrition. And of course, since these organism doesn't produce their own body heat as we can, they are depending on a suitable temperature for having activity. If it's too cold, they stop digesting the wood, and if it's too warm, they eventually stop the activity and eventually also die because they can't regulate the temperature themselves. And of course, the most visible factors is if it's a time span is long enough for having the activity going on so much so it gets any problem. Because if it's wet for just minutes or hours, it's not a problem. If it's a suitable temperature just for some hours, that's not a problem. But if those 3 factors are accessible for a longer period, for weeks, months, years, then we can expect to have a serious problem and caused by biological activity. This is very basic, but it's important to just understand what is the reason why insects or fungi are digesting wood. And you have to understand that wood is solid water and solid gas. The plants, the trees has combined carbon dioxide and water, and by using the energy from in photosynthesis, they can produce sugar molecules that can be longer and longer change, so they can produce the cellulose and the lignin structure. And by doing that, they release oxygen. But this is typically a reaction that can go both ways. When we have the wood and we have excess of oxygen and are deteriorating these molecules, it's releasing energy which the fungi and the insects are depending on. And while they are deteriorate the wood, they also release water as a damp and also carbon dioxide. So this is typically this photosynthesis and cellular respiration reaction is very crucial for understanding what's the reason, what's happening with the wood. Then the biodeterioration can be caused by 3 different processes. One is the the external enzymatic activity, and that it's typically fungi that, because they don't have any intestines, they don't have any mouth, they have to dilute the enzymes out in the surrounding area, and the enzymes is deteriorating the wood and giving the nutrition to the fungi. And in order to handle this, they need enough water in the wooden cells for this extracellular enzymatic activity. So deterioration occurs in each single wooden cell. And in order to have this activity, it has to be enough water in these wooden cells. And then the fungi can eventually cause serious decay of the wood, and by that also get enough nutrition for growing and producing new fruiting bodies and spores and then spread around. So they have a life cycle that is depending on excess of wood and water. And what's really happening is here we have dyed the fungal structure blue in microscope, but from these fungal strains, the cellulose, the enzymes that are breaking down the cellulose, is released in this aquatic environment. And then the fungi can get the nutrition from the deterioration, and it's also, the process is releasing carbon dioxide and water. But if it's too dry in this wooden cell, the cellulose wouldn't function, and then the activity of fungi are stopping, and so then it will be no further development. But typically the moisture is best conditions is inside the wooden materials. On the surface, it's the wind, surrounding air is drying out the surface. So the fungi has good conditions for development inside the material, but not on the surface. So it's typically inside the material we find this decayed wood, which has normally a typically brown color and this cubical cracking pattern. So if you're looking for fungal attacked wood, you can't very much rely on how the surface looks like. You have to look into the internal part of the wood. And the problem with this is that this requires more or less a destructive method for investigation. But of course, if it's a heavily decayed, the harm you do with your knife is not a problem because it's so much decayed from before. It might be that you see some fungal activity on the surface of the wooden materials, and that is very rare because, as I said, the surface is normally so dry, so you can't have any fungal activity there. But in environment where there is this very high, permanent high relative humidity, then the fungi manage to grow on the surfaces and manage to spread around much better on the surface and much faster on the surface than in the wooden cells. And that is typically for some special fungi like dry rot fungus, Serpula lacrimans, and the different Antherodia species that can manage to grow on the surface at very damp conditions. But as I mentioned, there are other processes that is causing biodeterioration, and that is when what is caused by the insects when they're eating the wooden cells. They digest it in their intestines, and then they have this internal enzymatic activity. That is caused by the insects which have the larva stage in the wood, and it's the larva that eats the wood, causing the damages, not the adult beetles, because the adult beetle just live for a few weeks and they don't eat at all, so they don't make any harm on wood, but they are producing new eggs that are giving larvae that can cause this further development of damages. So typically the insect activity is occurring inside the material, and the other only sign of any activity often is the emergency flight hole you see on the surface. And then theoretically the insect already had left the wood for copulating and producing more eggs. So it's larvae inside the wood that are eating small fragments of wood, getting into the intestines, and then it's a deterioration both by cellulose and some microorganism, and then it's the same result. It's release of energy and release of carbon dioxide of water. And the remain part of the wood that hasn't been digested is this typically boar dust, which is the excrement from the larva. And you can see normal the wood is deteriorated wood is full of boar dust when the insects are eating its way into the fresh wood. And the consequences of the activity is, of course, the more or less extensive deteriorated wood, and the strength has been strongly reduced. There are a third option in biodeterioration, and that is when it's not any digestion at all, but some other activity causing the damages. It might be woodpecker making holes for nest or for searching for food or just for making noise for scare away other rivals. Or it might be like ants who are using wood for a nest, and then they have to cave out the material in order to have a place to live. And you can find that in nature and as well as in buildings. And there are made some rodents that are just using their teeth in order to get through some wooden materials. You don't have to be a biologist to understand biodeterioration, but of course it's a very good advantage. But if you think that the reason for biological activity is as suitable by building physics in the building, and on the other hand you can turn it around and say that if you have suitable building physics, you can understand what kind of biology that will establish sooner or later. So this is two sides of the same coin, building physics and the building biology. And biodeterioration is a universal problem. I have been traveling around quite much and looking for damages, looking at damages in different countries. And even though it might be special species, special wooden materials, special constructions, and special climatical conditions, at the general level, it's the same reasons for the biodeterioration. So it doesn't have to be very complicated to understand this. If you have a general understanding, you can apply that to a different kind of environment and still get a quite useful answer. But of course, if you have the interest and you have the fascination for biology, then it helps, even though it might be quite tragic occasion with a lot of house dry rot fungus in the house. So an interest and curiosity is very good help for understanding the damages. And then it doesn't matter if the house is in Norway or in Japan, as in this case in Sapporo. We have the same building physics in the crawl space, and we have the same kind of excess of water, temperature, cellulose, and then of course the Serpula lacrymans species, the fungi, doesn't care if it's in Norway or in Japan. It's quite happy for digesting the wood anyhow. So if we can take one physical and especially mental step backwards, we can understand that even though it's quite different climatical conditions all over the world, there are some factors that doesn't change anyhow. And that is typically, we can see that if it's below 20% moisture content in spruce and pine, there is no risk for fungal activity. But the higher moisture level there is above this 20%, then it's an increasing risk for fungal activity. So by that with that background, you can expect it would be no problem at all in dry climate. But of course, if you look into buildings like this old building, you can see that even though it's very, very little precipitation every year, they have constructions for handling the water when it eventually comes, because otherwise the wood in the floors and wood in some constructions would be wet, and then it's a risk for biodeterioration. And of course, if you look at the temperature issue, you can understand that this is very optimal condition, even though it's quite dry there most of the time. But if it's a leakage into the construction, you can see the water has penetrated this floor, and you have both fungal attack and termite attack in the materials. So even though you expected that it wouldn't be any problem in a desert climate, it's really a danger anyhow. On the other hand, it might be very nice with a lot of water from rain and a suitable temperature. And then you expect it to be extremely difficult for preserving wood. But of course, it's always depending, does the wood really get wet or not? And if you can see, if it's raining and you see the lower part of the doors are wet, then you understand this is a critical situation. It will sooner or later be a deterioration. And something has to be done for repair the decayed wood, concrete or new wood or whatsoever. But it's interesting to see the reason for why the doors on both sides of the street getting wet is the water is coming to the roof and splashing down on the street and splash up again on the opposite side of the street. And of course, if you could avoid this event to happen, the wood would be standing quite dry, and then it wouldn't be any problem for fungal attacks. And when I was there, we found an old postcard. More or less, we found the postcard first. And this is from about 1920. And then we managed to track down the same street about 80 years later. And you can see the difference is here the roof has no protection for getting the water out in the streets, but formerly it was water drainage system for keeping the water from the street, and then you could expect to have much better service life of the wood, because you have a constructive elements that are keeping the wood dry, which is lacking now. And now we see an extensive decay problem due to this change of constructive elements. But where they still are remaining, you can see that the locally materials are standing very well, even though it's a humid, warm, tropical climate. If you go to Norway, we can see that it's not the same temperature. It's quite more cold climate, but still it's a lot of rain falling down every year. Here in Bergen, this is a World Heritage Site of Bryggen in Bergen. And this is buildings from early 1700. And with that kind of moisture exposure, you can expect it to be very fragile for biofungal deterioration. So even though the temperature is not so perfect, it would be a high risk. But the constructive elements are made for keeping the facades, the constructions so dry, so it wouldn't be any suitable conditions for fungal attack. It gets a bit wet when it's raining, but it's drying out very fast, and then it's not a problem in most of the surfaces and materials. But of course, if you come into some local areas where you have crawl space, when you have a low ventilation rate and you have a lot of moisture coming up from the ground, then you can reach a critical level, as you can see the green line in this area. But at the same time as room air just above the floorboards was quite much lower, and here is no risk for any activity at all. So we can see that the constructive elements can prevent from decay and also cause the higher risk for decay. And of course, if it's some water drain pipes are destroyed, and you get a lot of water on the wall, you can have extensive damages locally where the timber is wet due to this failure. But at the same time, the other wooden materials is standing quite well because they are not exposed to this extreme water intrusion. In Oslo, we have a bit less precipitation every year, but also a bit colder climate. And then we can find typically the damages are occurring where we have leakage into constructions. And as you remember this map, it's obviously we have a lot of biodeterioration in Oslo as well, even though it's a cold climate and not so much precipitation. But the damages are occurring when we have a leakage in the roof, for instance, like here, and water come into a construction where it slowly dries out. Then the fungi can have a very good development, even though the external climate is quite cold. Another example is in Russia and at Kishi. And here it's even colder. The average mean temperature is just above 0 degrees Celsius, and it's not so much rain either. So then you can expect it to be quite unfavorable for fungi to grow there. But still, there are some materials that are exposed to temperature, exposed to water, and then of course it can start to deteriorate. But then again, it's just part of the construction that gets wet and will get the deterioration. So it's not necessarily so extensive damages, but as long as you get water on the surfaces, it's a risk if the water gets into the logs and have a long, slow drying out process. And typically there, the church had originally a timber construction, and then they installed a cladding, and the cladding was protecting the timber structure. So the fungal attack that had started on the first time was halted by the cladding. But when the cladding was removed, the deterioration could continue because then it got more water on the timber construction again. Back in Norway, in the mountain area in with the continental climate, you can see the average temperature is quite low, and also it's not so much rain there. But it's wooden houses, and they have been standing there quite well. But you can see, even though it's a very cold climate, that locally there are some decay problems where the water is keeping the timber wet for a longer period. The exposed timber up in the air is drying out thanks to the wind, but lower part of the buildings might have a problem due to this snow and rain that is on surface and it's gathered together in local areas. And then of course you have a problem with biodeterioration, even though the climate in general is very harsh for fungi. The most extreme illustration of this is from Svalbard, Spitsbergen, which is about the most extreme you can think about. It's an average temperature of -6 degrees Celsius, and it's a really low amount of precipitation. So this is more or less a polar desert. But still, we can, when we go into the details of the buildings, yeah, it's very close to the North Pole. So it's, but there are some buildings from hunting activity, from mining activity, from the 100, 200 years ago. So we can see that it's extremely cold in general. So we wouldn't expect anything to happen there, but still. And this is summertime in the end of May. So it might be a lot of snow, even though it's summertime. But and we measured here. You can see the relative humidity was 93.7 relative humidity, percent relative humidity, and the temperature in this hunting cabin was minus 0.4 degrees Celsius. So it's very cold and it's a permafrost underneath. So it's not very suitable at all for fungal activity. But still, you can see here is ice, and this is fungi growing quite well. So there are some specialists that can grow at low temperature. There are some periods when the temperature is not so low anyhow, so the fungi can grow. This fungus is typically this one we find very much at Svalbard. It's Leucogyrophana mollis, so it's typically very favorable, have quite favorable conditions, even though it's cold in a sense for general approach. But if you start mapping the temperature in this hunting cabin with the air temperature at the time for 1.4 degrees Celsius, you can see that the different part of the wall had a bit higher and significant higher temperature due to the sun radiation. So it's not correct to say that this hunting cabin had a temperature of 1.4 degrees Celsius. It depends on where you're looking for the temperature. And as a matter of fact, in that area, it was so warm, so it was, as a matter of fact, too warm for any fungal activity, because it's a dark surface and the sun radiation gets the temperature very high. And it's fascinating to see that at Svalbard, it was we measured higher temperature than the average temperature at Zanzibar. So you can't only rely on looking at the map or by general impression of what the situation is. You have to measure it and you have to examine it in order to really be sure what is the correct situation. So in this roof board, I can go back, this one, you can see that inside this material is it's more or less a tropical microclimate. As long as it gets wet, it's fantastic for fungi to grow there. And this fungi we found here is Gliophilum sepiarium. It's like warm sun-exposed constructions in Scandinavian country. So this really shows that you have to look into the microclimate in order to understand the risk for biodeterioration. And even though it's very little precipitation, if it's a leakage somewhere, it can get a lot of water in one spot, and then you can have extensive deterioration in those materials. But of course, people there is not so concerned about decay fungi, because they are more afraid of other organisms that might be more dangerous in general. So if we look into combine the temperature and precipitation in these different areas, you can see that at Svalbard it's very low average temperature and very low precipitation compared with Zanzibar, and still we see that in general we can see that the biodeterioration is occurring more or less at the same speed because of the microclimatical conditions. At Zanzibar, the timber is very resistant, but also the climate might be very harsh, very humid and damp and warm. So we can see that many of those damages I've seen in Bergen, in Röros, Svalbard, Russia, Zanzibar, and other places, it happens within 50 to 100 years if it's outdoor exposed materials, because the microclimate might be much more similar than you first expect it to be. But then, of course, some damages is not really depending on the climate. If you have a leakage in the roof, if you have a extensive water intrusion due to some constructive error, then it will be a problem no matter what kind of climate you have. And sometimes you can see the construction is having so stable conditions, so it doesn't really matter so much of the climate, while other damages is really depending on what is the climate, what is the temperature for insects, for instance. There are no insect problem at Svalbard because it's not warm enough for the insect to survive there, but the fungi manage. So we have to understand what is the different reasons for deterioration. And the climate change is a very big issue in many countries. Of course, it really should be. But when it starts, when people started using modeling methods to predict what will be the future decay problem on outdoor exposed wood, then I have to say that this is completely wrong way to analyze things, because it's not correct. This is something that has been done by a meteorological institute in Norway with some civil engineer people, and they said that this is the situation today. It's a high risk at the coastal area of Norway, and it's a medium risk some other places, and it's a low risk in the mountain area. While they say that with climate change in 50 years, 100 years, we can expect it to be much more high risk for biodeterioration, fungal attack in larger part of Norway. But this is not correct with respect to modern science, because, and this is what, well, the main conclusion in my thesis from Dr. Philo's thesis is that's really importance is the microclimate. It doesn't matter what the climate in general is if the microclimate in a log, for instance, is favorable. As you saw in desert climate or at Svalbard, it's a local and really microclimatical conditions that is important. You can see this is from Estonia, a museum building that has been standing there, moved there 30 years ago. And you can see it's in the springtime, it's a quite dry log wall. But if you look into detail, you can see that some area is a bit wet due to rain and due to dripping from the roof. And we can go even closer. We can see that this is the area which is really wet. And the question is, how fast does it dry out again? If it's wet for weeks, months, then it's a risk for deterioration of the wood. So even though the building might look quite dry, it can be local areas that is critical for biodeterioration. Then, of course, it's not only fungi. It might be mold. It might be other plants that grows and causes discoloration, and it might be different reasons why it can be a decay by wood materials, even though they're not necessarily is eating it. So different reasons can cause a different kind of damages, but the main problem is that it's a biodeterioration. And that is something that's predictable. You know, if you have wet timber, you know that it will be some mold within weeks, some fungal attacks within months or years, and also wood-boring insects within years. So this is very predictable, and that's a very good advantage when we try to avoid problems in buildings. You saw this earlier. So we can see that on surfaces it's not very much to find of damages, but inside material we have much more extensive damage developing. And the reason is, just for repeat these 4 factors. If it's wood, if it's wet wood in a suitable temperature, it's just a matter of time before it has some kind of biodeterioration. So this is the figure you have to remember. And if you understand this simplified version of the conditions, then you can solve most of the problems in your own country. If it's mold, we're talking about mold, then it can occur on many different surfaces, and it can grow quite fast, just as I said, within weeks. And most of is a lot of different species, but most of them are requiring above 85% relative humidity in order to be able to grow. And the higher that humidity is, the better conditions it is for the fungi. So if it's completely wet, you can find mold damages perhaps within weeks. So the critical issue is to keep the wood dry. Then we have to understand that we really talk about microclimate. If you have wet wooden material, this blue element down here, it's a gradient from that wet material to the ambient room air conditions, but the gradient is very small. It's just like within a couple of millimeters. So if you have dry air in the room and a wet material, it doesn't help with the dry air, because the surface will have, you have a water film and you have a surface that is wet, and that is very much enough for fungal spores to start growing. So the gradient is very small, just within few millimeters, and that is a critical thing to understand when you are looking for moisture problems and you are measuring the room air relative humidity, because it's very easy to measure at the wrong spot and then you get the wrong answer. This is it's a modern glass fiber wall covering which has been painted by acrylic paint. It is occasionally it's condensation on this wall, and due to air circulation, the water condensed water is drying out. But if you look into detail between these two glass fiber strands, the fungi is growing in between, because there it's a bit longer time of wetness in this valley between these two small glass fiber strands. Even though it's just a millimeter lower than this surface there, it's quite enough for the fungi, because it has a bit better time of wetness in the on the surface. And if it can grow for 15 minutes instead of 2 minutes every day, then of course it's occasionally we will get some visible damages. It's not necessarily very important to measure every situation. If you can understand this figure, you're really expert in understanding the risk for condensation, because the temperature and relative humidity is two parts of the same issue. And if you alter one of those factors, if you change the temperature, for instance, in one direction, the relative humidity changed in the opposite direction. So if the temperature is falling, the relative humidity is getting higher. And opposite, if the temperature is rising, the relative humidity is sinking. And as a thumb rule, you can remember this, that if you change the temperature with 5 degrees Celsius, you approximately change the relative humidity with 20% in opposite direction. And this is a very, very useful knowledge to have. If you learn this one, you will be regarded as experts if you're not that from before in your community, because this is something that very many people have struggled to understand. And the practical issue is just an illustration of that. The practical issue of that is that you can see in this case a museum library with quite poor ventilation. In a room air, it was 75% relative humidity that summer with 20 degrees Celsius. And on a north-faced wall, on this behind this bookshelf, we measured 2.5 degrees Celsius lower temperature. And what would be the consequences of that? If you remember, I said that if you change temperature 5 degrees Celsius, the relative humidity would change 20%. In this case, we changed it from 20 to outside behind the books to 70.5 degrees. Then the relative humidity would rise 10% up to 85%. Then the question is that a problem? Well, you can look on the surface area to a room, and it's not a problem at all. But in this behind the books, when it's more stable, a bit more damp conditions, you can see, not necessarily very easily, but if you look more into detail on those books, you can see that there were some visible mold damages on the surfaces. So a good advice to look for mold damages is to use a parallel light beam on the surface. Then you get a relief of the mold that gives a very clear vision of the established damage, like here. So be active with a flashlight or use flash on the camera when you take pictures in some different angles, and then you might see the damages very clearly, even though it's not so visible for the naked eye. Then, of course, if you have the books with mold damages in a building, you have to start asking, is this a new or an old damage? This actual book was from 1770. The building was from 1770, and the book, as you can see down here, is from 1645. So in this case, the book was older than the building. So potentially the mold damage could have been brought into the building. But then you can just, if you go back, see that this is very fresh, new grown mold. So at least I can see that. So then you can understand this is something that had happened that summer. But as always with timber, with other materials, they can have, and people as well, one person can get a cold and another can stay healthy. And this typically, you have to understand that different, more or less similar materials can have very different reaction on an exposure for mold, for instance. You can see this book on the top is heavily infested by mold, and the next one is not at all. The next one not at all, but then again, one book is heavily infested with mold. So if you're looking for damages, you have to make a representative selection of surfaces you're looking for, looking at in order to find if it's a problem or not. And remember this. Sometimes it can be very strange damages, like this case. Here you can see that this wooden spoon in a museum building, unheated museum building in Norway, had extensive mold growth on one part of the spoon, but not on the other part. And at the same time, you can see that the floor, the table, the wooden table didn't have any mold growth at all either. So of course the temperature, the moisture, and the time exposure is the same. So the only different thing is the accessible nutrition. And as you can see here, the wood is not enough for the mold growth, but this spoon has never been washed properly after it was used last time. So this part has been used in some food porridge or something like that. So the remains of the old food substances is enough for the mold growth to occur. So in one way, it's not necessary to change the temperature, change the relative humidity, or that kind of physical aspects, but in order to remove the mold, you have to wash the spoon. But of course, then you remove some of the old food nutrition substances that could be interesting for scientists in the future. So don't uncritical remove all old dust, old surface treatment or so whatever on surfaces, because they might be a source for future information. This is a Another example of if it's not necessarily humidity itself or the temperature that causes the damages. Here is a cellar, a damp cellar under the building from 1700 and something, I don't remember now. But this is a floor up to the first floor, and you can see that some materials are old, original. Well, the building was from 1850 about, yes, and they are without any damages. But due to a leakage from the facade, some of the floor was replaced some months earlier, and the new material, the new wooden material that had been there for 5 months was without any discoloration, without any mold damages at all. But another composite wooden particle fiberboard had extensive mold growth within the same time of exposure. So you can see that in this case, again, it's not the temperature itself, it's not the humidity that is the problem. The problem is the use of materials that doesn't stand that kind of exposure. So using ordinary traditional spruce materials has proven to be okay, but these modern cheap wooden particle boards is completely hopeless in that exposure. And we see that differences between different materials in modern buildings and water damages. You can see the wood itself, the spruce, has no sign of mold growth at all, but this modern gypsum, gypsum boards, plasterboard, has extensive mold growth on the paper lining on the surface. So we have to understand that material quality has a very large impact on the risk for biodeterioration. And well, this is modern materials, but we did a test of growing mold on modern insulation materials. And you can see at 85% relative humidity, it wasn't any growth at all, except for the control material, pine. But if we raise the relative humidity to 97%, we got, as a matter of fact, mold growth on concrete, on rock wool, on glass fiber wool, and different extruded polystyrene and polyurethane foam. So it can grow, mold can grow on any surface if it's getting wet enough for long enough time. This is a scale of relative risk for mold growth on different kind of materials. You can see the gypsum board is wooden particle boards, and those kind of materials is high risk for mold growth. But on the other hand, you can see that inorganic materials, of course, is not very popular for mold, and it's a bit different between pine, heartwood, and sapwood, for instance. So quality of material has impact on the mold growth, and that's typically, you can see that this damp basement has been work relatively quite well for 100 years, and then by a fire regulation, the floor was secured by gypsum board in order to get fireproofing. But then in this exposure, within 1 year, the gypsum board was heavily infested by mold growth. So we have to understand, is there possibility for the different organisms to deteriorate cellulose? They will do that. And we have to understand what is the risk for that happening in different material quality, different exposure, different conditions. Because if the fungi gets the possibility to deteriorate cellulose and hemicellulose, it's very little remaining material in the wood. Only the brownish lignin is remain, and then the kind of decay is called brown rot decay. It's caused by very many different kind of species. And the problem is that even though it's a very low weight loss of weight of the of the timber due to fungal decay. If you lose 5% of the weight of the dry wood, the strength of the material is reduced by about 50%. And if you lose about 10% of the wood by fungal activity, more or less all strength is ruined by the fungi. So we can say that fungal attacked wood has no remaining strength. But then the challenge is to find where is the where is the damage, because we can't find it on surface. We have to go into detail and see where is the risk for any activity, both by normal fungi and more rare fungi, because this is the ruling or reason for the damages. So yeah, just have to understand that temperature is typically one important factor, and this can be seen very clear where you have log outdoor exposure, and one part is, well, the log is completely wet. It's a moisture content of far above the critical limit. And you can see one part of the log is without any damages, fungal decay, while the other part of the log is heavily decayed by different wood decaying fungi. And you can see that the reason for that is that you have sun radiation on this part. So in that climate at Röros, the limiting factor for many fungal activity problems is the sun, the temperature. So if in the shadow part it's so cold, so the fungi has struggled with growth, but on the sun exposed part, it's very favorable conditions regarding to nutrition, regarding to moisture and temperature, and the time for developing these damages. This had been happening in about 20 years. So we have to see where is the suitable situation for fungal attacks, and it's typically not on the surface, even though some elements, these fruiting bodies, are growing outside on the surface in order to spread new spores. The fungal activity are occurring in the wood materials. And we looked on this at Svalbard and other places, and we can see typically the same pattern is occurring everywhere. Internal part is decaying where it's wet long enough time. At Svalbard, you have this permafrost from the ground, and you have this thaw zone 20-30 centimeter normally, and then you have the air condition, and the accessible water is from permafrost and up in the air, and then it's dry out due to low amount of rain and wind. And the temperature, if it's sun radiation, might be on the air part of the wood and decreasing part down to the thaw zone, because at permafrost there is never any plus degrees at all. But doing measuring down in the soil from the surface down to the permafrost, we could see the typically gradient of, well, if we got completely down to permafrost, this was freezing, but then we had all the way, we had 100% relative humidity. So the accessible water was favorable all the places, but the temperature was a limiting factor. And with that physical conditions, we got the typically pattern of the decay, the yellow part of the materials, showing how the fungi managed to use the develop in those conditions. And this is also found in buildings in the mainland of Norway, where it's a shadow. It's not so favorable because it's not getting wet from rain, and it's not so warm from the sun either. So it can be big variation on the same wall if it's a high or low risk. And you can also see typically here at the surface is too warm due to the sun radiation, and also too dry due to the sun radiation and the wind. But just a few centimeters in the wood, there are more stable conditions with the temperature and humidity. And then we can see that it's typically internal decay pattern with an unharmed surface, while the heartwood of this material is, because this is pine wood, is without any damages. I mean, always the pattern of decay tells us what is the situation regarding humidity, regarding temperature, and by that we can understand why the damages are developing in that pattern. So we have to see where is it favorable temperature and maybe where is it too warm. Because if it's getting too warm, these dark surfaces in Oslo, this Oslo building, it's boil out the water and it's killing the fungi because it's too warm. But on the light colors, the surface is never getting too warm in order to dry out water and in order to kill the fungus. So we have to understand that we can see pattern in the building physics where the damages are occurring, and we can see pattern in different kind of species depending on temperature and constructions. This is not anything you need to remember in any way, but it can be interesting just to remember that in some exposure, as I mentioned, this Leucogyrophona mollis is very common on Svalbard, while other fungi is really struggling to develop there. But at the same time, at the mainland Norway, you can see that there are other species that are really most common in building. So you can learn a lot from the fungi as well, but building physics is the most important thing. We can also see where we have found the decay problems is that it's typically in floor, mainly down to basement and down to the ground, the crawl spaces, and of course external walls which get wet from precipitation. And if it's leaking in roofs, then we also find damages. So it's very predictable why the damages are occurring in those places, because the building physics will be that most optimal. So we can, just reading the damage as a book, really understand what is the reason for what's happening and what is the result and what is the solution for avoid this. We can understand almost any kind of damage, even though we have to make an adaptation to the specific case, like here in Svalbard. You understand that it can be very different microclimatic zones for possible growth for fungi, for instance. So, but this can be applied to any kind of building, as a matter of fact, from the southern wall, north facade wall, from the roof to the crawl space. So we have to understand that it is like a big jigsaw puzzle. A lot of different part of the building will have different condition. So we have to understand what is the risk, what is the real damage, and what is the solution. And as I mentioned, this border between unharmed wood and harmed wood can be very small, just a few millimeters can difference from between unproblematic situation and extensive damages. And you can see the pattern that microclimate is extremely important. And within this section of a log wall, you can see this is the right part is from outside of the wall. And you can see in this crack, water has penetrated through wind and precipitation. You can see that the less dense spring early wood is more attacked and decayed than the late wood, which is more dense wooden cells. So you can see microclimate is the most essential part for understanding the damage development. And this could be applied to the insects as well, not only fungi. We have to understand that they have the same kind of basic requirements, and that's the reason why we can have different activity, and from, well, termites at Zanzibar and other places to carpenter ant or other insects. So we have to understand what is the condition and how fast can it grow, because normally in cold climate, in a building with good ventilation, it doesn't grow very fast. It might be exceptional fast growth in few cases, but this picture to the right is not what we see every time it's a dry rot fungus attack in buildings. So it's easy to get scared if you just read what the worst case scenario would be, but normally it's not so bad, and it's all damages is handleable in one way or another. But we have to understand to see the whole picture, because if you see holes on the surface, it's easy to think, oh, this is some emergency flight hole from wood-boring insects. Maybe it's not this few holes, so it's not a big problem. But if we check this out better, so we can see that it's a brown rot decay, at least in the internal part of the log. And then we can also understand that these emergency flight hole is coming from insects that lives in fungal attacked wood. So this kind of damage will not, more or less, not be able to develop further than the decayed wood already had, fungal attacked wood already had been. But if you see something that looks strange, different, it very much can be solved by common sense, curiosity, and perhaps asking some for help. Some experts that could just look on the picture, say something about the risk for further development or consequences for measures. So you have to go into and look with open eyes and see what is possible to see. This log wall, you can see that most of the damage is in the lower part and also at the upper part. Not so much at the middle part of the log. And of course, with understanding that this roof has been repaired several times, the water is just falling down and splash up again. It's not surprising that these materials have been attacked by both fungi and insects, and partly up here also. So then something we can see the pattern, and then we can understand what is the possibility to avoid this kind of water exposure if in the future we can make sure that the water from a roof is not just falling down and splash up on the wall. Some drainage pipes or what is possible to do at least should be an option to find out in order to remove one of these four factors. If you take away one of them, there will be no further activity. Yeah, so then we also have a problem with all the established truths that people are talking about. They say that this beetle, house longhorn beetle, lives in dry wood. It's partly correct, but if you see into facts, they really, in optimal conditions, would like to have high relative humidity, quite nice moisture content, and a high temperature. So we see if they can survive in dry conditions, but that is not the first choice, and it will go very slowly. And you can also see if it's getting too warm, even though it might be damp conditions, the insects will eventually die due to the too high temperature. So the ecological conditions in Norwegian buildings is, it's not optimal for all insects, but it might be a possibility for part of the activity at least to use this temperature layers. But again, when people say they develop best in sun-exposed materials, and I say it myself also often, we have to remember that sun exposed is not an specific description. In this case, this part of the log, which had a lot of rain and a lot of sun exposure, I expect it to be a lot of house longhorn beetle damages, while here down in the shadow area, with little direct rain and little sun exposure, I expect it to be very little activity of insects. But as a matter of fact, these shadow areas was most attacked compared with the sun exposed, which was more or less without any damages. And if you have some measurements, if you see some diagrams of some temperature logging or something, it's so important to understand what can we read out of this information. This is a time of, well, 1 month logging in this sun-exposed log wall. And it looks quite nice. The red line is up in the sun, and it looks nice, favorable temperature for insects. So that would be very suitable for them. But then we have to remember that this is based on daily averages to get these numbers. If we look into the same data, but show it into hourly average, we can see that every day the temperature in this wooden surface is rising up to 35, 40, 45 degrees Celsius, which means that if you have a larva that had been managed to establish there, sooner or later there will be direct sun radiation that will raise the temperature in the timber so high that it will kill all the insects. So, but that is not possible to read out of this graph, where it's not hourly but daily average. And that's explain why we don't have that kind of insect damages there compared with the expectation. And we see the same in other buildings. When we start monitoring, we can see that due to this sun radiation, we get a high reading almost every day or several times a day. And that will cause so dry and warm conditions, so the insect will struggle to survive. Yeah, here you have this. You've seen that one. I thought you could think about it, but if you remember, it was the sun radiation that caused that possibility for the fungi to grow there. And again, we can monitoring and see that the sun radiation is at Röros is the limiting factor. So if you have this exposure that you can rise up to 20, 25 degrees Celsius, is much better than those materials that are exposed to 10, 15 degrees Celsius. So we have to analyze what is the optimal condition for the fungi, and vice versa, what is the optimal conditions for preserving the wood. And by doing that, we can make sure that we have as long service life as possible for the materials, even though we don't initially perhaps see the differences between different apparently similar conditions, because a wooden building and a brick building would have very different moisture temperature conditions. So we have to understand that even though they might have the same condition, we can find completely different damages due to the reason that they are the building physics are very different. So I always try to explain that if you look into a building and would like to see where is the risk for damages, what is the damages, what is the cause for damages, and what is the solutions for handling it, we have to take a mental and a physical step backwards to just get an overview of the building first. And when you have that, and we see that, okay, this part is quite nice, and we have the the main problem is down to the street here, when we have some water splashing up on the lower part of the wall, and we have some decay problem. When you have this general understanding, then we can take 2 mental and physical steps against the building and see if the first impression is correct, or if there is some extra factors we have to take into account in order to understand the complete picture. So I hope this was a good comprehensive introduction about the importance of microclimate. And with that hopefully a new knowledge for you, I wish you good luck further on.